Let's look at what we did in lecture number 2. So in lecture number 2, we went through the very basics of probability theory, and the very basic concept is there of the probability density. So if let's say Px is the probability density of some random event x, then Px dx integrated over a naught to let's say b naught, that gives us the probability that we find the particle between or the random variable between a naught and b naught. Then we look at the concept of ensemble average. Now what is an ensemble average? Well, first, what is the concept of ensemble, which is a very important concept within any random signal theory or statistical mechanics. So the concept of ensemble is as follows, that if we have an experiment and if we repeat the same experiment at the same time, then those copies or those different realizations of the same experiment, they constitute the realization, they constitute the ensemble corresponding to that variable. So of course the individual realizations do not have much meaning, and that is why we look for the ensemble average as a quantity, which is the most meaningful quantity. Now the ensemble average is defined as the sum of the outcomes in different realizations divided by the number of realization, and the ensemble average has meaning in the limit when n goes to infinity. Of course, in a physical situation we can have n a large number, and depending on what experiment, what situation is, how much is the how big n should be such that can be considered n, it also depends on the experimental situation. As a definition, we take this in the limit n goes to n going to infinity. Now in the situation when the probability density is known, then of course we don't need to have we don't need to know the outcomes in those infinite number of realizations. As long as we know the probability density, we can calculate the average. We also call it the expectation value, and it is given as the expectation value of x is x times the probability density dx, and then of course integrated over the appropriate range of the variable x. In addition to just calculate the expectation value of x, which definitely contains some information about the variable, we can also calculate the rth moment of a random process, and the rth moment is defined as the expectation value of x to the r if x is the random variable, and this is defined, the definition remains same. This time it is x to the r times the probability density dx. So that's the rth moment of a random process. Of course this contains much more information than just the first moment. And of course the first moment is called the mean, and the second central moment is the variance. Central moment is the same thing as the rth moment, but just defined from the mean. So it's just x minus mean of x to the r, that's the rth central moment, and the second central moment is actually the variance, and the square root of that is the standard deviation. Then we looked at the concept of the joint probability. And joint probability is the concept we require when we have more than two random variables, and joint probability quantifies the probability that both the random events happen together. So let's say Px1 x2, if that is a joint probability density of random events x1 x2 happening, then one can actually calculate the individual probability density by integrating the joint probability density over the other variable. Similarly, we can do P2 x2 by integrating the joint probability density over the variable x1. We looked at joint probability density also in the context when random variables are discrete. Well, if xi and yj are the two discrete random variables and pxi yj are their joint probability, then the probability density, these are all probability density, so in this case it will be probability, not probability density. So the probability that the event xi happens is the probability, joint probability of xi yj summed over j. Similarly, the probability that event yj happens is the joint probability pxi yj summed over I. Okay. Now, when we have just one variable, real or random variable, we have mean or the rth moment. But when we have two random variable, in this case I am taking two complex random variable, then one can define what's called two-time correlation function. So just like we have mean as x, then xr, when we have two random variable, the first quantity that can actually be defined is z1, z2. In fact, z1 star z2, and this I discussed last time. Well, although I didn't show it mathematically clearly, that this is, when it comes to random variable, one actually takes this kind of quantity which is z1 star z2, and not the other combination as z1 star z2 star or z1 z2, because this is much more meaningful quantity, and this we will see as we go along. We saw that when this two-time correlation function, this two-time correlation function is called the mutual correlation function, and when z1 is equal to z2, this function is the autocorrelation function. Okay, so this is what we did last time, and today, so these are three concepts I already discussed. Today we want to discuss one more concept, and which is the complex analytic signal representation, and this will be the last concept I will discuss for this part, and then we will go to kind of study the two-point correlation functions. So a few things about complex analytic signal representation before we get into the math. So the idea is, in a physical theory, one always studies the dynamics of real valued quantities such as current, charge densities, etc. And we also, I mean, it is always a kind of general observation. We know that the complex variables, they render mathematical calculations much more easier compared to real random variable. So within classical description, a real random variable is first mapped onto a complex random variable. The dynamical evolution is studied with the complex random variable, and at the end of a calculation, the physical quantities are extracted by taking the real part of appropriate quantities. So this mapping of real random variable to the complex ones is called the complex analytic signal representation of real random variables. In fact, the analytic signal themselves are purely mathematical quantities and do not necessarily have any direct physical meaning, but they make the calculations much easier. So the ease of the calculation, that was the motivation as to why the complex analytic signal representation was introduced. And again, as we see here, the idea was that you map a real signal onto a complex random variable, and then do the math with the complex variable so that it becomes easier, and at the end of the day, one just gets the real quantity out of that. So for classical signal, when it was introduced, it was for the mathematical ease, but it turns out that this process becomes the only way of doing things when it comes to quantum mechanics. Okay, we'll get to the quantum mechanics in a few lectures, but here let's see what is complex analytic signal representation. Okay, so let's say xt is a real function of a real variable, and let's also assume the Fourier transform of xt exists. If the Fourier transform exists, then we can write xt as, let's take the blue color. Right. So if the Fourier transform exists, then we can write xt as a Fourier transform, and for the time, the Fourier domain is the frequency. So I mean, probably most of you are familiar with the Fourier transformations. Fourier transformation is a way of writing a signal or a function in one basis in terms of a function in some other basis. So for example, here time, the conjugate basis is frequency, and there the basic functions are e to the minus I omega t. That's the basis we try to write this in, and the weightage of these ones, we represent that as x omega tilde, and this is summed over d omega integrated over minus infinity to infinity. So that's the Fourier transform of the signal xt. and most of you are probably aware of this. Now this can be written as, this is very simple, all we want to do is just split this integral, which is from minus infinity to infinity in omega, into two separate ranges. The first one is minus infinity to 0, and then we have x tilde omega to the minus I omega t d omega plus zero to infinity e to the minus I omega t d omega. So it's very simple. It's just writing this integral as two separate integrals. Of course, this is an integral over omega, so the whole thing will be just be a function of time. This also is an integral over omega, so this whole thing will be a function of time, and we can write as, this is equal to some, let's call this is the positive frequency part, so let's call this z of t, because this is complex, and this is, we use x when it's real, we use z when it's complex, and so this thing is then simply z star t. So we have xt, and we have written that xt as a function of z star t and zt, and this zt is called the complex analytic signal associated with the real random variable xt. So this is the idea of complex, very simple but very powerful. So just take a real signal, write its Fourier transform in terms of its conjugate, separate the signal in terms of positive frequency and negative frequency. The positive frequency part is z of t, and the negative frequency part is z star of t, and this z of t is called the complex analytic signal associated with the real random variable xt. Okay, now we'll now look at some of the properties and facts about this analytic signal. So first we realize that the zt itself can be written as a Fourier transform, because although zt was just going from 0 to infinity, so what we had is, let me take the pen. Okay, so what we had is that zt, this was equal to zero to infinity e to the minus I omega t d omega. So of course this is not the real proper Fourier transformation. For proper Fourier transformation we need to have the integral grow from minus infinity to infinity, but we can do that just simply by saying that this is equal to minus infinity to infinity some, let's say, z tilde of omega e to the minus I omega t d omega. Okay, and how do we define this new variable? This is basically z omega is equal to x of omega when frequency is positive, and but this thing is 0. When the frequency is negative. So just by doing this procedure, we can make sure that we have a Fourier representation of this complex analytic signal. Okay, so ZT is a complex analytic signal, and therefore it is single valued and has continuous derivative, and this is the way in which it can be written as in terms of a Fourier transformation. Okay, another fact, since xt is real, what do we have? There's a nice property that actually comes out and which we will use quite often. So I want to actually derive. This is very simple, but it's quite powerful. So we'll derive it here. Now, since xt is real, it simply means that x of t is equal to x star of t. Now, x of t we defined, x of t we want to just write as this Fourier transformation. So this we had written in the earlier slide just as signal in the other domain from minus infinity to infinity x tilde omega e to the minus I omega t d omega. And so what is x star of t? Well, x star of t is the x of t and star of the whole thing. So minus infinity to infinity x tilde of omega e to the minus I omega t d omega, and then this whole thing star. So now we can write this. We can write this as minus infinity to infinity. This x tilde becomes x tilde star omega e to the plus I omega t d omega. Okay, now we can write this now as minus infinity to infinity x tilde star minus omega e to the minus I omega t d of minus omega. This is simply by substituting omega with minus omega, and then since this is a minus here, okay, so I think this should be a positive infinity and this should be a negative infinity because we have substituted omega with minus omega. Now since there is a minus here, we can take that out and invert this limits on this integral, and then we can write this as this is equal to minus infinity to infinity x tilde star of minus omega e to the minus I omega t d omega. So now comparing this and this, we could see that the only way these two could be the same is when x omega is equal to x tilde omega is equal to x star tilde of minus omega. So this basically means or implies that x star tilde of minus omega is equal to x tilde of omega. So, well, this is a very important result. This basically says that the positive frequency part of the signal contains as much information as the negative frequency part. So negative frequency part doesn't contain any new information. I mean, the all the information that is there in positive frequency part is also there in the negative frequency part. So one can actually use either, and by taking the other one doesn't gain any new information. So that's what it means. So this is a very kind of important result, which we will keep using it again and again. That's why I sort of derived it here. Okay, so now there is a connection between the real and imaginary part of ZT as well, and that is what I want to look at next. So first of all, we have that the X, the signal X, xt, we know that we wrote that as the positive frequency part or the negative frequency part, that is xt as z of t plus z star of t, the analytic signal and its complex. So of course, if we add a complex number with its conjugate, then we end up with its real part and twice of that. So this quantity is basically twice the real part of zt. So what we have is that real part of zt, this is just simple, real part of zt is equal to half of xt. Okay, so half of xt is actually the real part of zt. Now let's denote that there is a imaginary part of zt as well, and let's say that that imaginary part is given as imaginary part of zt. Let's say that it is half yt. Okay, so that we can write zt, we can write zt as xt plus iyt. So that's a say. So this is the analytic signal, and in this analytic signal, the real part is the real signal that we are concerned with, and of course there will be an associated imaginary part, and that's yt. And it actually turns out that one can actually show, I am not going to show it, but one can actually show that this real part xt and imaginary part yt, they actually form a Hilbert transform pair. So xt can be represented as this, yt is this, and where p is called the Cauchy's principal value, defined as this. I am actually not going to go into the details of it, but I am just mentioning it here as one of the properties that comes out in this complex analytic signal representation, and this is very useful in several contexts. In several contexts, in the wave propagation, when one tries to save the faster than light propagation, there it actually becomes quite useful. I mean, one actually uses it, but again, we are actually not going to be using this in this course, but this is a very nice property to kind of remember in the context of complex analytic signal representation. Okay, so that was the basics of complex analytic signal representation. Now we want to see now how this can be utilized for what we aim to achieve in this course. So what we have in this course is that we are concerned with the real classical electric field due to a chaotic source, and let's say that that field is, we represent that by some random signal VRT. And this R here, this basically says that this is a real signal. So some source with a lot of emitters, and that's the field, that's the random signal VRT that actually comes out, and then again this R is to remind that this classical field is actually real. Now we will try to represent this real signal in terms of a complex analytic signal. So I am just going to repeat myself here. So there is nothing, whatever we did for X, we will now do that for V, and then we will see as to how this complex analytic signal representation, how that yields some meaningful quantity. So what we have here is this V, and R I am putting for signify that this represents real, and this R is the coordinate. This is the vector, this is just a scalar t, and so this we can write as a Fourier transform, and so this is t here. So again we'll go to the frequency space, so minus infinity to infinity. I'm just repeating myself here, whatever we did for x, we'll do that for v here, and v is our classical real signal. We can call it electric field as well. So this is r omega e to the minus I omega t d omega. Of course, this integral is from negative infinity to infinity. Now we can break this up as two separate integrals. One goes from minus infinity to 0, v tilde r omega e to the minus I omega t d omega plus the positive frequency part, and that goes from 0 to infinity. And the same thing, v tilde r omega e to the minus I omega t d omega. Okay. Now this part, this is the positive frequency part, and that's the negative, this is the negative frequency part. So we will call this part as this capital, this is a V without any R, and this part we'll call V star RT. So this real classical signal that we have written in terms of V star RT and VRT, this is the positive frequency part, and that's the negative frequency part. So VRT is then the complex analytic signal corresponding to the real random variable VRT. Now we know, of course, we took this signal to be real, hence this we just derived, this V star R minus omega will be equal to V R omega, just because this is real. Again, saying that the negative frequency part contains precisely the same information that the positive frequency part contains. There's no new information that is hidden in the other frequency range. Okay, now with this, I'm just rewriting it, VRT as V star RT and VRT, and these are the definitions of the positive frequency part and the negative frequency part. Now let's say what useful quantities we can define using the complex analytic signal VRT that corresponds to this real signal VRRT. So the first quantity that we can define, and that one likes to study in random signal or in any, is the intensity. So how do we define intensity? Intensity is defined as, that we all know. So intensity is defined as I at some location r, again r is a vector at some time t, and this is defined as V star with a RT V RT. So the complex analytic signal and its conjugate, you multiply them and take the ensemble average. That is the intensity. So if you don't take the ensemble average, just this quantity V star RT VRT, this is what's called the instantaneous intensity at RT, this location, this space-time point. But when we do, and of course this is not something that can be measured, this is instantaneous intensity. No matter how fast a detector is, one always accumulates a signal for some time period, some finite time period. This is just a concept, this is called the instantaneous intensity, but the quantity of interest in any experiment is this expectation value, in which one calculates the average value of this quantity. Okay, now the next quantity is the cross correlation function. Here in the intensity, again we have a product of we have product of this V star and V star and V, but these two quantities are at the same space-time point, but we can have another quantity in which we have these quantities at two different space-time point, and in which it's called the cross correlation function, and it is defined as follows. We call it we write it by symbol gamma and define it as gamma R1, that is the first point, T1, and R2, T2. This is how we represent it, and it is defined as the expectation value of V star R1 T1 V R2 T2. So this is the expectation value which is expectation value of V star R1 T1 V R2 T2, and this is called the cross correlation function. This quantity, this is actually a very important quantity, and this in the entire second order coherence theory we will actually be studying this. It quantifies the visibility of interference fringes produced by superposition of fields at R1 T1 R2 T2. This we will look at in much more detail. So similarly, we can then just continue defining higher order correlation functions in the same manner, and the next higher order correlation can be a 4-point correlation function, where we have taken fields at R1 T1, R2 T2, R3 T3, R4 T4, and the first two are star and then two non-star. Now within classical theory we will not discuss 4-point correlation functions much, but of course it exists there, but we will not be discussing it. But within quantum entanglement we will actually be discussing in quite some detail, and this is the quantity through which we quantify two-particle coherence, and that two-particle coherence is intimately connected with what's called two-particle entanglement, and we will do that in much more detail when we take up two-particle coherence and entanglement. So this kind of concludes the basics of stochastic processes that we require, and one of the most important thing here is this complex analytic signal representation. And once we have that, then it is all about just finding the expectation values of these quantities. The first quantity is the intensity, where we have taken the fields at the same point, V star RT, VRT. Next up is cross correlation function, where we take it as the 2 points, R1 T1, R2 T2, and then we can go higher. So this methodology will continue in classical, then one particle quantum mechanics, and then two particle quantum mechanics. The methodology that we develop for finding just the mean or the rth moment, that is the same methodology that actually kind of continues, and then we will see how it goes further. So then in the next class, in the next lecture, we will start studying this cross correlation function in detail and see why it is relevant, why one studies it, what is the way of studying is, how to actually measure it experimentally, and so on. So I'll finish the class here. Thank you so much.